This is a few transistors that I have up here. And of course, what I have is I have my uh, meter set to the p-n junction scale. People call it the diode scale, but actually it's the p-n junction scale. And of course, now the polarities of my meter match the leads, right? So this would be a positive voltage, and this would be a negative voltage. And what it does, it displays the voltage that's required to cause the thing to conduct. So this is the lead. This is some transistors here. And these are some TO92 cases, right? I showed you all the cases, right? So these are the ones that we'll be dealing with primarily, even though they come in a lot of different styles and shapes. This is a TO3 case. Of course, basically, you can tell the current carrying capabilities by the size of the transistor. So the bigger the transistor, the more current it's rated in, right? We could look this up. This is a 2N6552. These transistors now, so where's my 3 leads at? Yeah, which one? Which lead, which lead, collector, emitter, or collector gets the hottest, dissipates the most heat? The emitter only drops 7/10 of a volt. It's not going to produce, yeah. The collector is the one that current's running through that is reverse biased. So the collector is the one that's dropping all that voltage. It's the collector, right? You understand? It's the one that gets the hottest. So this is the collector. I know this is the collector right here, right? And then one of these has to be the watt, one of them has the emitter, and one of them has to be the base. And we'll show y'all how to identify that. So if I've got one of these, this guy right here, I don't know what the current rating is on it, but it's got a metal tab on the back of it. That's going to be the watt, the collector. So on these, I can find the collector real easy. I can just put my ohm meter across here, and I touch the leads. So what does that tell me? Well, this don't make any difference because the collector is connected to one of these leads down here. And how much resistance would the collector have? Collector to collector? None. So it don't make any difference which lead you lose down here. Now we're gonna have the lead makes a difference when we start identifying which is the base and which is the emitter, right? You understand that? So right now I know the center lead is the collector. Y'all hear that? So now I can come over and touch this one. And let me get out of the way so we can see my meter. So I know this is the collector. So I'll just leave my positive right there. And I'll touch these leads right here. I get an overload right there, give an overload right there. So what do you think I need to do? Switch the leads. So I'm going to put my negative right there. And then I'm going to come over here. And I'm going to touch the leads. Okay. That's one of them. That's one. Okay. So I don't get anything there. I get something right there. So what do you think this lead right here is? I can't afford bias. I cannot afford bias from collector to emitter. If I try to measure between collector and emitter with my ohm meter, it'll always measure overload because I have no base current. If I have no base current, then that basically means what? It means the transistor's open between watt collector and emitter. So this can't be the emitter because I'm measuring a voltage drop. This is the base, right? Okay. So that means this over here has to be the what? The emitter. So I'll get my meter leads out of the way. I want you to notice something. This is very important. So we know this is the base. I know this is the collector. It's measuring 0.549 volts. This is the emitter. It's measuring 5.51 volts. This is the collector. This is the emitter. I got my positive on base, my negative on the collector and emitter. So what would this be? Would it be a PNP or an NPN? I got a positive on the base. That's the guy that's in the middle. So this is the base. So what type of transistor is this? NPN. I'm putting my negative on the emitter, and I'm putting my negative on the collector. What do you notice about the measurement between the emitter and the collector? 5.51 volts on the emitter, 5.5 on the collector. So what we're going to find out, and you're not going to find this in the book, guys, but the emitter will always measure slightly higher than the collector because it's highly doped. It's got a lot of electrons in there, right? So it'll measure slightly higher. So that's the way now we can identify all three leads. The emitter, the base emitter, will measure what? Slightly higher than the what? Base collector. So this don't have that tab. So I've got to figure out, okay, what is this? First of all, what is this? So what am I going to do? This transistor right here. I'm just going to randomly choose a polarity, and I'm going to put it, I usually put it on the left lead, and then I'm going to touch the other two leads. And what do I get? I get nothing, right? Everybody understand that? So what am I going to do? I'm going to touch my leads. I'm going to touch the other two leads. I get nothing there. Hopefully I get some. So I started off here, right? Nothing here. Okay, sorry. I didn't touch it. I touched right there. So if you start off with one lead, you use the positive, and I touch the other two leads, that finds what? Nothing. And then I swap the leads. I come over here. Nothing here. Nothing here. Swap my leads. I got a junction there. I got nothing here. A junction there. So what does that mean? I have a PN junction right here. I know it's silicone, by the way, right? I have nothing right here. I have a PN junction right there. So what does it mean? Well, what I'm going to do is I'm going to leave my plus lead where I found the junction at. I'm going to leave that alone because that's going to be the base. I notice when I go, I measure 6.51, 6.52. I go here, I measure 6.4. So there's my junction. 6.5 right here, 6.4 right there. This is your emitter right there. Y'all see that? Huh? Yeah, this is my emitter if I don't touch them. 6.51 here. That's the collector. I've got P on my base. I'm putting 2 in my collector and emitter, so this has to be NPN. Everybody okay? Yeah, plus on this guy, this is my base, so that's a P on the base. I put an N on the emitter, and I put an N on the collector, so this is a NPN, right? That makes sense? I'm going to do the same thing on this one. I'm going to touch, I'm going to start off with a red lead. I'm going to touch right here. I don't see a PN junction. I'm going to touch right here. I don't see a PN junction. I'm going to swap my leads. I'm gonna touch here. I see a PN junction. Touch here, I don't see anything, so this is gonna be my base. I'm gonna come over here, right here. I measure a PN junction, so I don't keep touching my legs together. I'm gonna measure right there, I measure nothing. I keep getting in front of my meter, guys, I'm sorry. I should be using a piece of wire right here. So this looks like it's my base, but when I come over here and touch this side right here, make sure I'm touching it because I was messing up. It measures an overload. This guy measures a junction. I need to give you a piece of wire. This guy measures a PN junction, right? Let's see what I'm doing, right? I keep flopping my leads, and my meter leads are now in the coil. Okay. So here I measure a PN junction, right? I'm gonna come over here and put this right here. I measure nothing. Oh, wrong. Thank you. Here I measure a PN junction. Here I measure nothing. So what does that mean? We started off here. I started off here. I went over here and I put my red lead right there. I measured a nothing, and I measured a nothing right there. Swap my leads. Now, if I measure something on both of them, I just identified my base. If I measure a PN junction on one of them, that is the base. Everybody understand that? So I'll come over here and put that right there. I know that is the base. Everybody okay? So that means if I go to my other side, I should measure a PN junction right here, but I measure an overload. So what do you think that means? It's bad. That's exactly right. Huh? Yeah, so it's bad. We know this. Either this is not a transistor, it's not a BJT, or it's bad. Two directions, between the emitter and between the base and the emitter and the base and the collector. You should measure about 6/10 of a volt for silicon and about 3/10 of a volt if it's a germanium diode, germanium transistor. Now, some of these guys, they identify the leads. Like this package right here, I can't remember what it is. And I'll pass this around, see if I can see all this. But because number one, that's an approximation, and here the only current flowing through the PN junction is the current that's provided by this meter. It's not being provided by a 12-volt power supply that might have 15 amps available to it. So your meter has very low current is capabilities to it, right? You understand that? And what it does, it just starts raising the voltage until it senses a current flow. So when we say 7/10 of a volt, is that true? It's an approximation. Number one, it's approximation. So normally, the bigger the current, the less the VF is. So if I come over here and look at this guy right here, okay. Now I'll come up here. I know which one's the collector. I know this is the collector, right? So I come over and touch both sides. I don't measure anything. I'm gonna swap my leads. Okay. Now I know this is the base. Now this sucker is heavily doped, so it's not even dropping. It's not even close to 7. It's dropping what? Yeah, about 500 millivolts. Yeah, if I can get it. Yeah, about 500 millivolts. So that 7/10 of a vote is just approximation. Now, why do we use 7/10 of a vote? Why, when I look at a resistor and it's color coded, when it's color coded brown, black, brown, why do I say it's 100 ohms when I know it's not? It's approximate. So that 7/10 of a vote is a what? It's approximation. And your meter is not going to measure exactly 7/10 of a vote. It's going to give you what exactly is required to cause this thing to start conducting. Right? You understand? And normally on these transistors, the more current that it's designed to handle, it's going to be on the lower side of 7/10. The less current is going to be probably on the upper side or right around 7/10. That makes sense now? So that 7/10 is an approximation. But it works because we know our math is perfect, right? You understand? But what's the problem with our... So will my calculated values always equal to my measured values? Never. Unless you're in DC. And what did y'all do in DC? You measured all the resistors. You didn't use the color-coded value. You measured the resistors because you was trying to prove Ohm's law. But once you understand these things have tolerances, you know your math is perfect, but your components are not. So every equation that we use, when we say that thing drops 7/10 of a volt, in real life, it's probably not going to drop exactly 7/10 of a volt, right? But it's going to be what? Close enough so our circuits work the way we think they're going to do. So that's a good question. This is also an NPN. This guy is not even, this guy 200 millivolts most away because it's a high current. And so what happens is when they start getting into these high current or these high wattage transistors, then normally they're going to take that collector and connect it to the metal so we can heat sink it, right? You understand that? So this is obvious where the collector is at. The collector is this metal right. This guy right here, we don't know the collector. We know the collector is connected to that chunk of metal right there. Now, what advantage does metal have over plastic as far as dissipating heat? Metal dissipates heat a lot better than plastic. Yeah, but it dissipates heat a lot better, right? Plastics is an insulator, but plastics are insulators. Metals are not, and thermal resistance follows almost the same line as electrical resistance. So plastics, we use plastic as insulators. So plastics are not only insulators against pushing voltage current through, right? You understand that. It's also has a lot of thermal resistance, which means it's hard to get rid of the heat also, right? Metals, though, they have what? Metals have very low thermal resistance. So that means in which lead is this metal connected to? It's going to be connected to the collector because the collector is the one that's reverse bias, right? You understand? So it's the one that dissipates most power. So if we see one of these transistors, I know this guy has to be the what? The collector. So if it's got 3 leads on it, then I can find the collector real easy. I can do it. So I found the collector. I've got my meter on continuity check, right? And also diode check. So there's the collector. So now I can touch both leads. I know now the one that I touch has to be the base. So I know that guy right there has to be the one. Has to be the base. So I know this guy over here has to be the emitter. So if the diode's good, you should get that base to emitter. You should get that forward bias voltage on 2 leads, right? If you only get it on one of the 3, then it means it's what? It either means it's bad or it means it's not a transistor, not a bipolar transistor. This one, though, what's nice about this one is this guy right here. Let's see if I can see it. Y'all have to pass it around. There's a tab right here. Can y'all see the tab? It still don't show up, does it? Oops, let's see if focus in. Oh, yeah, it's hard to see. There's a little tab right there. This identifies the emitter, so it means this right here is the emitter, and this is the base. But if you look, you don't see the little insulator around here and here. Here you don't see the little insulator, so this is connected directly to the cage. What lead is that? That's the collector. So these guys right here, you can identify the leads. But we still need to be able to check. You understand? So this is. Oops. Oh, wait a second. So there's a p-in junction between this lead. There's a p-in junction between that lead. I got my positive base, so this is also in. So this transistor, we would say it's good. So what we do, even if we know the lead, we still can use our meter to check to see if it's what? It's good or bad. Here's another case. So here's what Brian does. So this guy, you know the leads on this one. So this one has a flat side to it. So there's a flat side on this one, and it's parallel or perpendicular to a lead. So this would identify the emitter on this one, and then the offset one would be the base, and the other one would be the collector. So some of the transistors identify the leads for you by the package that they're in, and then other transistors, those where the leads are coming out the bottom, those could be any arrangement. But we should be able to do what? We should be able to identify which is the emitter. So the base emitter voltage should be what? A little higher than the base collector. Everybody understand that? So what we have up here, guys, this is the lab. Here's the transistor. Four up here. Yeah, this is an FET. Here's the lab. Working teams, which I need to turn we have other transistors